Today I will introduce the results of a research that I carried out with my colleague Jyrki Savolainen from Finland. I'm from Italy and I work at the University of Trento. So in this research we took into account what could be the effects of putting together multiple simulation modules into a digital twin in order to manage the operations and maintenance of a mining industry. Let's see, first of all, what do we mean with digital twin simulation? To be clear, we didn't have the opportunity to study a real digital twin. So what we did was to simulate one. So with the digital twin, we defined it a multi-domain simulation model that would integrate operations and maintenance, simulation optimization. So this part allowed us to reproduce the effects of our decisions in terms of maintenance of physical assets with an overall profitability simulation of industrial operations. So we put together this module with a second module, which simulation module, which was able to replicate financial aspects of a mining industry. So the goals of the research were substantially two: to investigate the general properties of a cost simulation framework, so to integrate optimization and system dynamics, which are a bit different tools, and this was to investigate what was the economic profitability given some decisions about the maintenance policy for our equipment. So, and the second one was to develop a numerical experiment, a simulation of a digital twin where we could examine these effects numerically. We chose the metal mine example because my colleague Jyrki have experience in this field, and he worked for several years in the mining industry. So let's see a bit better what do we mean with a cost simulation system. So we thought, okay, we can replicate what is at the equipment level, the things that are happening in a real environment. So for example, you can see here we have several trucks that are made of different components, and these equipments are unreliable, meaning that they could break, they could fail at any time. So they need preventive maintenance to be kept in good condition and to run more efficiently. Our production system level was made of showways, trucks and workshops. So trucks and showways were simulated as agents, and they could decide whether to undergo maintenance. So they had to move to a workshop, and then they could go back to work. And we then considered some macroeconomic variables to see what was the effect of our operations on the profitability of the whole mine. There were therefore these aforementioned two simulation modules. The first one was the optimization module, which allowed us to replicate the effects of a time-based maintenance policy on a fleet of showways and trucks which operate within the mine. And this was realized using a discrete event simulation of maintenance policies. So substantially, what we were able to, at least an example of what we were able to do using these simulations was to investigate the effect of the frequency of maintenance. So the more frequently we perform preventive maintenance on the equipment, the higher the cost of preventive maintenance, but the lower the number of failures. On the other hand, if we perform preventive maintenance very rarely, we will have a lot of corrective interventions. And as you can see here in the plot, there is a minimum, so there's always a good condition, a good balance between corrective and preventive maintenance. This is instead, we had on the other end system dynamics module, which allowed us to take into account the financial operability model of the mine, where we implemented some macroeconomic variables, and we could experiment a lot with the uncertainty about the cost of maintenance and what were the effects of these variations, of these uncertainties. So to schematize what we realized in our digital twin simulation, as you all know, digital twins lies in between a virtual space and a physical space. So in our virtual space, we set it what we called a maintenance policy selection. So where we took our decisions about how frequently to maintain our equipment. Then we had the system design, so equipment with nominal capacities, which are all the parameters that we considered for the equipment. And this allowed us to produce a high fidelity model of the operations in the mine. The data that we used, that we produced from this module, were then used to feed a low fidelity profitability model, which is the system dynamic module that I mentioned before, which allowed us to understand if given a specific maintenance policy, we were operating profitably. So we could eventually refine our search for different parameters of the maintenance policies, and then to optimize in a feedback loop this maintenance policy. We could then use our simulation module to replicate a single run of the experiment, and to verify what was the effects of economic uncertainties, which could be like the microeconomic variables like the spot price of the ore, or the uncertainty about the costs of maintenance. So what we carried out were two experiments, one about the design of the mine, how many trucks and how many shovels to use, and what was then the effect on the profitability. So we were able to draw some conclusions about availability and utilization of the mining equipment. The first conclusion was that maximizing mill utilization and production throughput would yield the highest expected revenues, regardless of the price variations, and then that simulation-based digital twins modeling can perform an overall operational optimization while considering the stochasticity and high dimensionality of operational data. So I leave you with our last slide. Sorry, I have to skip these slides. If you are interested to know more, here there are the references for reading the paper. I think we finished the 8 minutes, so I hope to be on time. Thank you, Simon.